We're ready to learn some more matrix arithmetic. This is section 3.3. I can understand and perform matrix multiplication. Matrix multiplication. Now, we learned about scalar multiplication last time, but matrix multiplication is different. So as the warm-up here, we're going to talk about whether or not these matrix operations are possible. So we'll just look at each one of them. If it's possible, we don't need to calculate the resultant, but if it's not possible, we do need to say why it's not possible. So let's take a look at this one right here. This is a subtraction problem. Remember, dimensions are important here, so we need to do this element by element, and we need to check and make sure that the dimensions of both of these are the same. So 2 rows, 3 columns, 2 rows, 3 columns. This would be possible. So we'll just write that this is possible. Again, we're not going to go through and calculate that. This one right here, this one is a 2 by 3, and this one is a 2 by 2. So this one is not possible. So we'll just write not possible here. And then we need to include a reason for that. So it's not possible, and here's why. Not same dimension. And I'm going to write DIM for dimension. So there's our reason on that one. Now, matrix addition, subtraction, and scalar multiplication, those were all pretty easy. Dimensions were important for each one of those, as we saw up here. But when we learn about matrix multiplication, which is what we're going to do today, it's somewhat more complicated, and dimensions are even more important. So we're really going to have to pay attention to the dimensions. Matrices can only be multiplied under certain circumstances. And those circumstances are the number of columns in the first matrix. So let's write down columns here. The number of columns in the first matrix must be the same as the number of rows in the second matrix. And the resultant has the same number of rows as the first matrix and the same number of columns as the second matrix. So we're going to look at a couple of examples first, and all we're going to do here is we're just going to figure out, would it be possible to actually multiply these matrices? And if it is possible, we're going to state what the dimensions of the resultant would be. So determine whether the matrices can be multiplied. So here's what we need to check. The number of columns in the first matrix must be the same as the number of rows in the second matrix. So this is the number of columns in the first matrix. This is the number of rows in the second matrix. Since those are both 4s, we can multiply those. So the answer on this one is yes. And the dimensions of the resultant would have the number of rows of the first one and the number of columns of the second one. So this would be a 3 by 2 as the resultant. So let's take a look at this one. We've got matrix C that's a 4 by 3 and matrix D that's a 3 by 2. Let's check this number of columns with this number of rows, and those are the same, so that means the resultant would be a 4 by 2. So on this next one, this is example C, but it's got a star by it. So these are the same C and D, but now I've switched the order. What we want to check here, again, is the number of columns in this matrix with the number of rows in that matrix. You'll notice that those are not the same, so we're just going to write not possible. Not possible right here, because those don't match up. So my question for you is matrix multiplication commutative? Can you move things around like you can with regular old numbers? And the answer to that is no. Matrix multiplication is not commutative. So if two matrices can be multiplied, here's how we do it. Each element of the resultant is found by multiplying the elements of the corresponding row and column and then adding them together like this. So this is a 2 by 2, and this is a 2 by 2. So we can multiply these together. The resultant is going to be a 2 by 2. And each one of the elements is found by doing this. So for this first row and first column, we take the first row and the first column, and we've got A times E. There's the A times E, and B times G. There's the B times G. And then we add them together. So let's take this one right here. Second row, first column. We take the second row and we multiply it with the first column. So we've got a C times an E. There's the C times E, and we've got D times G. Now, that's just the formula for a 2 by 2, and writing down the formulas for a 3 by 3 would look even worse. It looks like a complete nightmare. So if that seems a little bit overwhelming, we're going to simplify this by thinking of this as what's called the karate chop method. So here's how we do the karate chop method. The first thing we do is we determine the dimensions of the resultant. And for the element in the first row and the first column of the resultant, we karate chop the first row of the first matrix with the first column of the second matrix. And then we multiply the corresponding elements, and this whole corresponding idea is really important. And then we add the results, and then we place that number in the first row, first column of the resultant. Now, I know this sounds really complicated regardless of which method you think of here, or which concepts you're kind of applying. So we're always going to do three things before we multiply matrices. So here are those three things. We're going to check the inner dimensions first to see if you can actually multiply the matrices. We're going to determine the dimensions of the resultant, and then we're going to draw brackets and a blank space for each one of the missing elements in the resultant. Now, it really is easier than it looks and easier than it sounds, so we're going to give this a try. So let's take a look at this problem right here. So example 2a. So here's the first thing we want to do. We want to check the inner dimensions and make sure that we can actually multiply the matrices. So this is a 2 by 2, and this is a 2 by 1. The inner dimensions are the same, so that means the resultant is going to be a 2 by 1. So we're going to write down a 2 by 1, and that 2 by 1 is going to look like this. So I'm going to make it fairly large so we can have space here. So a 2 by 1 has 2 rows and it has 1 column. So all we need to do is just find these guys right here. So this is how we're going to do it. We're going to chop the first row with the first column. This element right here is in the first row, first column. So we're going to take the first row and multiply it by the first column. So what I'm going to do here is I'm going to say, okay, to multiply these correspondingly, we're going to multiply the 1 with the 1, and we're going to multiply the 4 with the negative 2. So we do 1 times 1, that would be 1. So I'm going to write this up here. And then 4 times negative 2, that would be negative 8. So when we put those together, we get a negative 7. So negative 7 is going to be the answer there. So I'm going to erase this right here and erase this right here. And now we need the second row and first column. So I'm going to chop the second row with the first column, and we're going to multiply these in corresponding order. So I'm going to multiply the negative 3 with the 1, and I'm going to multiply the 0 with the 2, the negative 2. So this is negative 3 times 1. So I'm going to go ahead and write down a negative 3 right here. And I do the 0 times the negative 2, so this would be plus 0. So the element right here is going to be what we get when we add these together, so this is going to be a negative 3. So this right here is the answer there. Now, if you don't need to show the work on the sides, that's totally okay. I'm not going to do that all the time, but I'm going to leave that right there, and we're going to move on to the next one. So again, first thing we do is we check the inner dimensions. So this one is a 2 by 2. This one is a 2 by 3. So the inner dimensions are the same, so that means the resultant is a 2 by 3. So I'm going to draw a nice big 2 by 3. So 2 rows with 3 columns. And again, writing down these little blanks helps me remember, okay, where am I in this process? So let's go ahead and take a look at first row, first column. So I'm going to chop the first row with the first column, and I'm going to multiply these correspondingly. Now, I'm not going to do this all the time, but we're going to do it on the first couple here. So we're going to do the 2 times the 1 and the 4 times the 0. So if we do 2 times 1, we get 2, and 4 times 0, we get 0. So this would be a 2 when we add those together. Now I need to do first row, second column. So it's still going to be the first row, but now I need to do the second column. So, whoops. So I'm going to highlight this one right here. And we're going to do this correspondingly. So we're going to do the 2 with the negative 1, and we're going to do the 4 with the 2, and we're going to multiply these together and see what we've got. So we do 2 times negative 1, so that's negative 2. 4 times 2 is 8, so we've got negative 2 plus 8, so that's going to end up being a 6 right here. So I'm going to go ahead and erase that and erase the highlighting right here. And then this is going to be, let's see, first row, third column. So we're going to highlight the first row, third column. So we're going to multiply the 2 with the 0, and we're going to multiply the 4 with the 5. So 2 times 0 is 0, 4 times 5 is 20. So this element right here is going to be a 20. Okay, now we're going to move on to the second row and first column. So second row, I'm going to take this second row here, and I'm going to multiply it by the first column, and we're going to do this correspondingly. So the 1 times the 1, and the 1 times the 0. So 1 times 1 is 1, 1 times 0 is 0. So 1 plus 0 is 1. So we've got a 1 right here. Now I'm going to keep that second row highlighted right here. And we're now in the second row, second column. So second row, multiplied with the second column. So we're going to multiply the 1 with the negative 1 and the 1 with the 2. So we have a negative 1 here and a 2 here. So we end up with a 1 right here. And then we've got second row, third column. So second row, third column. And we'll multiply the 1 with the 0. And we'll multiply the 1 with the 5. So this is going to be a 0 when we multiply the two of these together, and a 5 when we multiply these together. So we end up with 115 for that second row. So I'm going to go ahead and circle this right here, and I hope that gives you a good sense of how to do these at this point. I'm not going to be highlighting from now on. If you need to highlight or do something like that, that's totally okay. We do need to stick with this method, though. It's a very good way of making sure that you get the answers right. So on this one here, we've got 2 rows and 1 column, and then we've got a 2 by 2 over here. So you'll notice those inner dimensions are not the same, so this is not possible. Not possible right here. So let's flip the page over and let's take a look at the ones on this side. Whoops, went a little bit too far here. And let's ask a question here. Is a dot required to show multiplication? Well, we can use implied multiplication with matrices just like we do with regular old numbers. So we don't need a dot between there. We know this is multiplication. So let's take a look at what we've got here. This is a 2 by 3. And this is a 3 by 3. So the inner dimensions are the same, so the resultant is going to be a 2 by 3. So I'm going to go ahead and write down nice big 2 by 3. And again, 2 rows with 3 columns, and then we'll just fill this in. So as we go through here, I am going to just do a quick highlight on a row and a column, but I'm not going to use the other colors. So this is going to be first row, first column. So we're going to chop the first row with the first column. We're going to have a 3 times a 1, which is a 3, and then we've got a 0 here and a 0 here. So we just get a 3 on that one. This is going to be first row, second column. So we're going to chop the first row with the second column. Whoops. First row with the second column. There we go. So we're going to have a 3 times a 0, a negative 1 times a 1, which would be negative 1, and a 1 times a 0. So this is going to be a negative 1. And then we're going to do the first row, third column. So we'll highlight the first row and the third column. And we've got a 0 and a 0 and a 1. So this is going to be a 1. And now we move on to the second row, first column. So second row, first column. We've got a 0, we've got a 0, and we've got a 0. So that's going to be a 0 right there. And then we've got second row, second column. So second row, second column. And we've got a 0, a negative 2, and a 5. So we've got a negative 2 right here. Change colors here, so a negative 2. And then we've got the second row, third column. So second row, third column. We've got a 0, we've got a 0, and we've got a 5. So I'm going to put a 5 right here. Let's go ahead and circle that, and we're done there. Okay, on this one right here, let's take a quick look at this. This is fairly small, but watch what happens with this. We have 2 rows and 1 column, and we have 1 row and 2 columns. So the inner dimensions are the same, so we can multiply these, but we end up with a 2 by 2. So we've got 4 different elements that we need to find here. So we're going to take the first row and first row and multiply it with the first column. So this is 3 times negative 3, so that's going to be a negative 9. Then we're going to do the first row, second column. So this would be first row, second column there. We multiply those together and we end up with a 12. Then we're going to move on to the second row, first column. So second row, first column. So we end up with a negative 6. And then we're going to do second row, second column. So second row here, second column there. We multiply those together and we get an 8. So we had fairly small matrices. We had a column matrix here and a row matrix here, and we end up with a 2 by 2 for the resultant. Okay, so that's how you do those. And I want you to take a look at example D up here. It kind of has an interesting answer. We took this 2 by 3 and we multiplied it by a 3 by 3, and we ended up with a 2 by 3. And if you'll notice that this 2 by 3 right here, the resultant is exactly the same as the one that we started with. So what that means is this second matrix acts like a 1 when we multiply. So it acts like a multiplicative identity. Okay, so that's why this is called an identity matrix. And we actually have some notation for things like that. So this right here, this 3 by 3 identity is called I3. So that's an identity matrix. And I2 would be a 2 by 2 identity matrix. I4 would be a 4 by 4 identity matrix. I'm not going to take the time to draw that, but you'll notice that they've got ones down the diagonals and then zeros everywhere else. Ones down the diagonals, 0 everywhere else. So if we were to draw an I4, an identity 4 by 4 matrix, it would have ones down the diagonals in a 4 by 4 and then zeros everywhere else. And an identity 1, an I1, we can draw that one because that would just be a 1 by 1 with a 1 right there. And that kind of makes sense. So let's slide down here and let's talk about a couple of thought experiments. So the first thought experiment is this. We've already established that matrix multiplication is not commutative. So would matrix multiplication work on these two matrices right here? So R is a 2 by 2 matrix and S is a 2 by 2 matrix. So we're going to go ahead and we're going to figure out what we get when we multiply here. So this is a 2 by 2. And this is a 2 by 2. So if we do R times S, the inner dimensions are the same. We're going to end up with a 2 by 2. So I'm going to have 2 rows with 2 columns. So this is what I need to fill out. And again, I'm going to try not highlighting here. So let's see what we get. When we multiply the first row with the first column, I'm going to multiply the 3 and the negative 2. So that's a negative 6. 2 and the 0. So that's a 0. So we get a negative 6 right here. First row, second column, so first row with the second column. So this is going to be a 3 and a negative 2, so that's going to be a 1. Then we've got second row, first column. Second row, first column, we're going to multiply these two together, so that's a 2, and those two together, that's a 0, so we just get a 2. And then this is going to be second row, second column. So second row multiplied with the second column. So the negative 1 and the 1 make a negative 1 and the 0. So this is just going to be a negative 1 right there. So that's what we get for the answer on that one. And again, notice the inner dimensions are the same even if I switch the order. So we're going to end up with a 2 by 2. So let's go ahead and write down what we get here. So I'm going to put a blank for each one of those. So first row, first column. So first row with the first column. So we're going to multiply these together. So this is going to be a negative 2 times a 3. That's negative 6. 1 times negative 1. That's a negative 1. So this is going to be negative 7 here. Now I'm going to stop right there and notice that if these were going to end up with the same result, they'd have to have the same dimension, which they do. This is a 2 by 2 and this is a 2 by 2. But they'd have to be equal element by element. And we've already messed that up because this first row, first column, those are not the same. I'm going to check one more. Let's check this other one. Let's check second row, second column. So second row, second column. This is going to be a 0. And that's going to be a 0, so we'd have a 0 right here. So there's no way that these are the same. So yes, we still think the same as we did before, and this just emphasizes the idea that position plays a huge, huge role when we're dealing with matrices. You can't just move things around within a matrix elements, and you can't just move things around when you're doing the arithmetic. It does make a difference on some problems, so please be aware of that. The second thought experiment is kind of leading up to some stuff that we're going to do later on. We haven't said anything about division yet. Okay, well, it turns out we can't divide matrices, but there is kind of a clever way to get around that. And to give you a hint of what it is, I want you to look at this equation right here. So this is 5x equals 30. Now, most people would just go through and they divide both sides by 5 and then get x equals 6. That is the answer, but here's the tough part. Could you show that 6 is the right answer without dividing, without using division? So stop and think about it. How would we get rid of that multiplying by 5 without using division? There is a way to do it. If you can come up with that, that's pretty awesome. If not, we'll show you when we get there. Okay, go ahead and do the self-assessment and get going on the assignment. Good luck. Thanks.